Thank you all for coming. My name is Brendan Hassett. I am a professor of mathematics here at Brown University, and I'm also the director of ICERM. ICERM is the Institute for Computational and Experimental Research in Mathematics. We're a research institute at Brown, supported through the National Science Foundation, the Simons Foundation, Sloan Foundation, Microsoft Research, and many other funders. We're really interested in the connection between mathematical research, mathematical ideas, and computation. We love cases where computations and data lead to new mathematical discoveries, and we're also interested in how mathematics can lead to algorithms that are useful in a wide range of pure and applied fields. We're also interested in how math and algorithms can interact with society, and so we're very pleased to have Adam Kalai here to give this lecture. So Adam Kalai did his undergraduate work at Harvard and his doctoral work at Carnegie Mellon. He did a postdoctoral fellowship, an NSF postdoctoral fellowship at MIT. He's been a faculty member at Georgia Tech and the Toyota Technological Institute. Since 2008, he's been at Microsoft Research New England. He's currently a principal researcher at Microsoft Research. His work is in machine learning, human computation, and algorithms. One of the papers that I found on Google Scholar, which I think is a sort of a precursor to what you hear about tonight, is an algorithm, like they used to have in the SATs. Man is to computer programmer as woman is to homemaker, debiasing word embeddings. And so I think he'll tell us a little bit about how we eliminate that kind of bias in computer systems. Thank you, Adam.
Well, thank you very much for inviting me. It's a pleasure to be here. And I'm going to be talking about, I'm at Microsoft Research, and I'm going to be talking about some joint work that I did with several talented interns, Maria de Artiega and Alexei Romanov, and some high school student interns as well, and several colleagues and at Microsoft Research and LinkedIn and other places. And the general picture is that as computers are getting more intelligent in human-like ways, they're also becoming more biased in human-like ways, and we need to work on that and figure out how to address that. Oh, by the way, there's a URL here. If you want to give feedback to me, and if there's something that I say that offends you, or there's suggestions you have for how to make the talk better, feel free to fill out this form. I would really appreciate it, actually, and I'll get anonymous feedback. So that's a good way to tell me how it's going. So I'll start right away with the takeaways, so you can leave if you're not interested. So the takeaways are that, as I said, AI is becoming more intelligent in human-like ways, and it's going to learn human-like biases. And these biases need to be addressed. Otherwise, you might think, oh, it's just the data, but actually it can be a problem if you don't address them, and we'll show how. And we'll discuss algorithms that will help us figure out who are the groups of people that you might be afraid your algorithm is discriminating against, and how you might address that. But I'm optimistic, hopefully, that in the long term, it'll be easier for AI algorithms to be debiased than it is for humans. So some people say, you shouldn't do this. Like you'll never replace a judge. A judge writes a decision and can justify their reasons, and you can ask the judge, why they made their decision. But a computer could eventually be a judge potentially as well, and a computer could give a decision that we could also audit and inspect. I'm not saying that will happen today, but computers tend to be fairly honest, and as you'll see in this talk, they're very straightforward with their biases in a bad way, but also that's good because you can inspect them and understand and change them in ways that might be easier than humans. So I'm not going to be talking about judges today. I'm just going to be talking about recruiting, which is also an important domain, and there's a lot of interest, as you might have read, about AI and recruiting. There's also a lot of concerns about AI being used in recruiting, and there are people who think AI should be used in recruiting, so it's an interesting and important area. So I'm going to start out by talking about gender bias and its geometry in terms of vectors, and then in order to understand whether that is important or how that would be important, I'll talk about a data set we've created for recruiting or simulating recruiting. And then I'll talk, as I mentioned, about what if you don't know, you're not just worried about discriminating against different genders, but you're worried about discriminating against other groups, races, and ageism, and things like that. And then I'll give the algorithm that is designed to address that. So starting with the paper that you were referring to about the geometry of gender bias. So let's talk about binary gender for simplicity. And well, actually, before I start, let me just start with that. Let me just talk about what a word embedding is. How many people here have heard of a word embedding? Okay, a lot of people, but not everyone. So word embedding is trained on billions of tokens or words, usually from the internet or from news. And it's kind of like a spreadsheet. You can think of it as it's a matrix, actually. For each word, it represents each word as a vector of some 300 numbers or so. And similar words should have similar numbers. They should be located near each other in the embedding. And it has millions of tokens, but for words, maybe 25,000 words is enough to cover the common words in a language. How is a word embedding trained? Well, you might think similar words, it just looks for words that are located near each other. But that's an oversimplification. It's not just saying which words tend to occur near each other, because two words might be quite related but not occur near each other. So it actually looks for patterns, common patterns. So it might find in one document that Boston is the capital of Massachusetts, in another document that Providence is the capital of Rhode Island. And it will use those to make all kinds of associations, that there might be a relationship between Boston, Massachusetts, and Providence and Rhode Island. And also, even though they're in different documents, that Boston and Providence are somehow serving similar roles because the words that they're around are similar. I'm not going to talk a lot about how they're trained, but that's the rough idea. And it can actually learn the relationships, which is really neat, and I'll illustrate that so you can see what's going on. Okay, why are these useful? Why would this be useful for recruiting? Well, suppose somebody is searching through a pile of resumes to hire a computer programmer. And suppose that the computer programmer doesn't use the word computer programmer on their web page, but she uses the word software engineer or Java, Python, and things like that. So the word embedding knows, it's kind of like a thesaurus, it knows that computer programmer is similar to software engineer and Java and Python. So it might be able to bring up these resumes, even though they don't literally have that word. However, the word computer programmer, so that's the smarts of the system, but the word computer programmer might also be far from the word Jane. So it would actually be comparing all these words, and that could be a problem, right? If we don't want to filter people based on their name, we don't want to use that. So you say, okay, I'll scrub the names, I'll remove the names from these documents, but even then it's not enough, because there might be words like softball or names of colleges which might indicate somebody's gender or race, and so that person might be pushed aside in favor of somebody else, where because of the sport they played or the university they went to, you can guess their gender or their race. By the way, I'm very happy to take questions during the talk. So if you have a question, just blurt it out or raise your hand, and I would love to have an interactive discussion as we go along. So this has been known for some time, and there was some very nice work. People got excited about it, especially starting in 2013, because the computer started doing really well at answering analogy questions. So because of this structure in word embeddings, there's two things I want to talk about. One is proximity, that similar meaning words, or all the city words will be near each other, all the state words will be near each other, things like that. Similar meaning words tend to be near each other. That's called proximity. And the other one is parallelism, so that actually the difference between analogous pairs of words tends to be parallel vectors. Okay, so you can just do a simple algorithm to try to find analogies where you take the difference between, if you want to know, Massachusetts is to Rhode Island as Boston is to what, you can just find this fourth spot in the parallelogram and find the closest word, and sure enough, it's Providence. And people love that because it's kind of an intelligence, a type of intelligence that the computer wasn't showing before. So this is just trained from the raw data on the web. And then you do it with Texas, and you get Austin, things like that. You can, so they went on and on. So the first thing we did is we just asked a very simple question. We said, okay, let's just start with only 2 words. Instead of starting with 3 words, let's just start with the 2 words she and he, and search through all the words in the embedding for other parallelograms, other pairs of words whose difference is very similar to she and he, she minus he. Does that make sense? And it came out with a lot of analogies. So some of them weren't that surprising, like she is to sister as he is to brother. But some of them were terrible, like he is to doctor as she is to nurse, yeah. And then he is to computer programmer as she, and you wouldn't even guess, but in the title of that paper, it was homemaker. So when it came out with that, we were really upset and said, this is a problem, because these word embeddings are used in all of these, all of the new apps or any application that is using language, if it's trying to use a language intelligently, it's using these word embeddings, and they're used all over the place, and this is actually what the word embedding has inside when you look closely. But some of them were really kind of wacky, like he is to WTF as she is to LOL. That's a good guess, but almost. Anyone else? OMG, that's it, yeah. Or she is to feminist, like he is to, this is an interesting one, realist. That's interesting. Or some of them were funny, like she is to pregnancy. What's the male analog of pregnancy? Anyone have a guess? What's that? Expecting. Oh, yeah, that's good. It was kidney stone is what the computer came up with. They're all sort of painful expulsions. But really it came out with hundreds and hundreds of these analogies. So unlike a person who won't even, wouldn't even feel comfortable saying one of these analogies, the computer just came out with hundreds of them, and we evaluated them by crowdsourcing and kind of going over, and people were looking at these analogies, and and sure enough, people could identify these as stereotypical and offensive analogies. They weren't just random. So I'm not going to discuss our evaluation of all these analogies, but suffice it to say they were, as I said, sort of stereotypical analogies and offensive. One simple way to measure the bias is actually what we did is we just looked at all kinds of profession words like homemaker, nurse, receptionist, which we found in the embedding. And then we asked people what gender stereotypes they associated with those profession words, and there was a high correlation of 0.5 with that. In follow-up work, some other folks, Koliskin et al., did something smarter. They just took the statistics from the Bureau of Labor Statistics. Oh, about 80% of the time I can. And they found a 0.9 correlation with the gender demographics of professions. So that was a very high correlation between what's in the embedding and both sort of stereotypes that we have and statistics that we have about gender demographics in general. Okay, so that just more evidence that the biases we have are consistent. Then what do you do about that? So one way to think about it is this word embedding. It's in 300 dimensions, as I mentioned, or several hundreds of dimensions. So I can't show you that, but I can show you maybe 2 dimensions. So in the vertical dimension, well, let me just show you 1 dimension that's important. Let's take the words she and he. We can always rotate the embedding so that she is on top and he is on bottom. Right? And then we have all these words, and we really don't like the fact that words like genius and hero are closer to he, or knitting and cupcakes are closer to she. Now that may depend on the application, but let's say we're talking about in the context of hiring, we don't really want to hire people based on their gender pronouns. The simplest thing to do is literally to just collapse this dimension, just remove this dimension out from the embedding with a trivial vector operation, and then she and he are on top of one another, and every other word is equidistant. It's not any closer to she or he than before. Does that make sense? Are there any questions about that?
That's a principal component.
We could have found the principal components of the embedding, but well, actually, okay, so this is, what I'm illustrating here is a slight simplification. What this is just taking literally the vector difference between she and he and zeroing out that direction. What we actually did in the paper is we took 10 pairs of words like king and queen, she and he, brother and sister, and found the principal component of those 10 sets of vectors and then zeroed out that direction. There was an analysis we did trying to figure out whether the gender bias was in 1 dimension or was it many dimensions, and then we ended up just taking the principal component and zeroing out the dimension. But this works, and actually in the rest of the talk, we'll just zero out he minus she.
What sample will you take to get these words?
Good. So this is a word embedding. So there's a lot of word embeddings that are made publicly available. This was one. This example is from Google. So they Google trained an embedding on like 6 billion words from Google News. So this embedding is actually taken from Google News, and in this example, I'm just taking the embedding of the word she, the embedding of the word he, and just zeroing out, making them the same, just moving them together so that she and he are on top of one another. Does that make sense?
Have you done it with foreign languages?
I have not, but I know people who are working on that. One of my co-authors, Maria de Artiega, is working on that in Spanish. It is a very interesting question what will happen, and that's one of the open questions, because in some other languages, gender enters in much more serious ways, because even the conjugation of verbs can be gendered and things like that. Great questions. Any other questions? We actually have a more advanced version, which I'm not going to talk about as well, but where we, what we do is we find that we try to keep the definitional words. So some words are gender specific, like brother and sister. So we actually went through the dictionary and found that there was a direction in the embedding where the embedding also had a sense of which words should be gendered by definition and which words shouldn't, and you can keep some of the definition if you want. But in the context of hiring, I think it's good enough to just get rid of gender altogether, in my opinion. So some people might like this because, you know, unfortunately, it's the analog is having definitions, you know, in a dictionary with gender-specific words in there. Now we don't have that, and why don't we want that? I mean, it's kind of obvious, I think, but it's worth going through that. Because some people will look at this embedding and say, well, you know what, I don't want to get rid of that dimension. That's the data. Just keep it. If it's in the data, keep it. But there's a problem with that, and that's what I'm trying to illustrate here. The problem with that, it would be similar to why don't we want to have in a dictionary to say, oh, computer programmers are typically male, nurses are typically female, because you might say, well, dictionary should reflect reality. No, because people use, why are they, you know, using a dictionary? Well, maybe a child is going to learn about that, and you don't want the child to then, you know, amplify those biases or compound what they're reading in the dictionary with what they see. What the dictionary is supposed to reflect is the definitional meaning of them, and these word embeddings are used by computers in a similar way to understand the definitional uses. So in this sense, I would say this is bad because because it compounds the bias. So if there's bias in the dictionary and you see bias in the world, it'll make it worse. Sorry. Okay, so next I'll talk about this data set. That we created, again, with these interns and collaborators, Alexei Romanov, Maria de Arteaga, and several colleagues at Microsoft and LinkedIn. Because we wanted to have a data set for hiring, but you don't actually have public data for hiring, right? The kind of profiles, that's very public, private information, and we want to have reproducible results. So what we did is we collected a data set of bios from the web. These are public bios. So here's an example. I just gave this talk to Bill Gates earlier this week, and so we have this fun example, which I thought I'd reuse, of Melinda Gates. She's a philanthropist. So her bio on the web says she's a philanthropist, and then there's a bunch of text afterwards. So in our data set, the goal is to classify the person's title from the text afterwards. Does that make sense? So we're trying to predict the word in blue from the green text. Okay. Now, we didn't actually have philanthropists in our data set because there weren't enough. We didn't use that because there weren't enough philanthropists in the world, unfortunately. But we had 28 other titles. And so we have this data set where we're trying to predict the green from the 28 titles. So the most common title is professor. There's a lot more professor bios on the web than any other title. It's because professors like to talk a lot and put their bios in the web, not because there are more professors in the world than janitors or something. But here's the demographics. There was kind of like almost an order of magnitude, not quite, but a lot more professors than anything else. We have interesting titles. And so what can you do? So now this is kind of the magic of word embeddings. Okay, so why do people like these word embeddings? You can actually classify somebody, you can use word embeddings to classify people without any labeled data. So if you were in a startup, right, you would download one of these pre-trained word embeddings, which has all the words and their vectors, and then let's say you're in a startup and you're trying to advertise jobs to people, right? Actually, during this project, one of the interns got an email from a headhunter who had gone, reached her webpage and sent her an email saying, oh, you might be interested in this job. And probably there was an automated, I think it even said in the email, there was an automated system that identifies these web pages and matches them to jobs. And so that's a very common thing. And so if you're working in a startup, you don't have tons of labeled data of people and their jobs, but you can use a word embedding to classify almost like magic without any labeled data. So what you do is you take the words and you look at their embeddings, and I'm only showing again in 2 dimensions, but suppose you take the words and you look at their embeddings, and then you take the centroid of the embeddings of the words, just the average of the embeddings, and then you embed all the titles, and you take the title which is closest to the average of these words, and you can use that to classify somebody's title from their bio just by splitting it into words and taking the average of vectors. Does that make sense? Was there a question? Okay, and then this is surprisingly accurate. So here I'm showing you 3 different word embeddings. One of them is from the web, and two of them are from the trained on the web, and one of them is from Google News. But anyway, all of them give you pretty high accuracy. So this is around 60% accuracy or above 50% accuracy. Now there's 28 different titles, so if you were guessing at random, you'd have a 1 in 28 chance, about a 3 or 4% chance of being right, and there is already 50 or 60% accurate, so somebody in a startup might be just very happy with this result, and and this is, again, this is without any labeled data, so it's nice. So you're just taking you're maximizing the similarity. Okay, so I said the smallest distance. Actually, formally, what we're doing is we're maximizing the cosine similarity, the inner product between the title and the sum of the words.
What happens if you guess professor all the time?
So in this case, first of all, this metric that I'm talking about accuracy is balanced accuracy. So what that means is I imagine reweighting the data set. Great question. I reweight the data set so that all 28 slices have equal representation. So you would have 96% accuracy. Sorry, 4% accuracy if you guess that. Yeah. The maximum of it means you're choosing the title that maximizes. You're predicting the title that maximizes the similarity to the words in the embedding. It just means, like here it would be the closest. Which one is the closest? It's not the distance, but which one is the closest? Which of these blue terms is the closest? If I said the minimum distance, it would be literally the length of that line. Argmin tells you which one is closest. Does that make sense? But think of it this way visually. If the equation doesn't make sense, don't worry about it. Okay, and so what do we want, though, from these systems? It's kind of tricky. There's actually a gazillion different definitions of fairness out there. In this context, what we're going to talk about, the one we've chosen, is we talk about accuracy gaps. So we're talking about the difference in the true positive rates between, let's just say, if we're talking about gender, by the way, there's more than 2 genders, but let's just talk about male and female. We're talking about the difference between the accuracy on females and males, meaning among females of a certain title, what's our accuracy and compared to the accuracy among males of that same title. And then we call that the gender accuracy gap. Okay? And in our data set, one of the convenient things is the bios are always written in third person, so you can figure out what whoever wrote it thought their gender was. Does that make sense? Are there any questions about this definition of gender accuracy gap? We would like to have a similar definition for race, but again, race is very hard to define in the first place, and we can't measure it very easily from the bios. We don't have the data. So we're going to use the gender to design and understand our algorithms, but we have algorithms that we hope will also reduce the race bias, but it's just harder for us to measure that. Okay, and this, there's many other aspects that are important in fairness. We might have biased noise. Our data set might have way more professors than we have in the real world. There's all kinds of issues that come into play, but we're not going to discuss those for now. Okay, so what happens when you look at this data set, when you run that simple classifier? So does the debiased embedding help us? That's what we're actually going to figure out in a second. So first of all, let's just look what happens. So the professions, on the x-axis, I'm plotting the different occupations here, and the x-axis shows you the gender balance, right? How many males and females do we have in our data set, or people who are using the she and he pronoun. And so nurses, as you can see, for example, are mostly female according to our data and the Bureau of Labor Statistics, and similarly, software engineers are mostly male. And then the y-axis tells us the gender accuracy gap. So let me just illustrate. So we have, first of all, we have, as I mentioned, many more female nurses than male nurses. And the fact that the gender accuracy gap, this is the difference of accuracy on females minus males, so it's positive, so it means we're more accurate on females. So we're more accurate on the female nurses than on the male nurses. And software engineers are down here. And again, we have more male software engineers, and we're fair bit, like 15% more accurate on the male software engineers than the female software engineers, so we're making more mistakes. And we call this compounding. When we're in the lower left corner or the upper right corner, we call that compounding. Why do we call it compounding? There's already a difference. There's way more male programmers than female programmers in the world to begin with. And if we're advertising jobs to the male programmers at more often than to the female programmers, we're contributing to making that problem bigger, right? So that's a problem. Does that make sense? So we would have liked everything to be on the 0 line, equal accuracy for males or females, or at least no correlation between them. But you can see the trend, there's a strong correlation between things here. So for many of the professions, we're compounding the bias. Does that make sense? There's a gender balance on the x-axis, the gender gap, a gender accuracy gap, and the correlation means that we're compounding the bias. Okay. Now, then we can check and see if we use one of these debiased embeddings where we've removed the he-she direction compared to a regular embedding, does it change? And it doesn't make things perfect, but you can see that it reduces the gender accuracy gap. So this is for the 3 different embeddings I was mentioning. All of them, you have the gender balance and the gender accuracy gap. And for all 3, the gender gaps go down, and they're much less correlated with the gender balance. For the
that's unfortunate.
by removing the, yes. We're happy that it happened, but it might not, you mean? Well, it didn't go all the way down to 0, first of all. Yes, yes. I mean, in hindsight, it's not surprising it's good. Sometimes we've tried many different things, and some of them didn't work like we were hoping, to the degree we were hoping. Well, this is a bigger effect than you get if you just remove the names and the pronouns. Okay? And I was hoping that it would go further, but anyway. There's also a lot of different possible definitions of what fairness means. So, for another thing it doesn't work is it doesn't equate. We were hoping that these differences between the male, there would be no gaps. Anyway, I'll be happy to tell you later what other things we tried. Okay, so this is all without any supervised data. So if you're a small startup, you don't have data. But if you're a big company, you might have tons of data, and then you might do actual learning to say, okay, well, I'm going to try to predict this person's title from this huge data set that I have. And similarly, here what we have is I'm showing you for 3 different types of learning algorithms what happens if you remove the names and pronouns. So there is a question, it's not obvious to people whether you should remove names and pronouns from your data set when you train and when you test. Does that make sense? So you have all these bios. They have all kinds of clues about people's gender. Should you remove them? What happens if you do or don't? And your accuracy doesn't change at all. So these are the things that, like, it's not obvious. You might think, oh, shoot, if I remove the names and pronouns, my accuracy is going to drop a ton. It actually changes just by like less than, or around 1% maybe. It was very little overall. But the difference in accuracy between men and women goes down a lot. Does that make sense? So that's good news. So I would support removing pronouns from the data set. And these are, if you're training a very deep neural network, or if you're training a simple bag of words model, or if you're using word embeddings. Okay, and there's kind of an analogy here. Well, as I mentioned, though, before I do that, these are not perfect. Just removing the names and pronouns does not get rid of this correlation. You still have a lot of bias. What's going on? So the analogy is, I don't know if many of you have heard this, but they used to have orchestra auditions just regular, and then they changed it. They put a curtain between the person who's auditioning and the judges to make it blind auditioning, and the fraction of females went way up as a result of that. But there was another subtle point. They actually had people take off their shoes as well because they realized that when women would walk in high heels, even though the curtain was there, you could still kind of detect that it's a female. And the analogy I'm trying to draw here is that just removing the names and pronouns doesn't necessarily totally mask from the computer the gender or race or whatever of the person. So we can actually look at that and see that specifically in our data, which is kind of neat. So if you look at the words, you can see how much mutual information they have with labels. So if you say, among men, how informative is this word about their title? And among women, how informative is about this word about their title? Separating men and women. So then the most informative words are something like doctor and university. Well, that makes sense. If you tell me that they have the word university in their title, that gives me a big hint about their title. And the least informative words are something like he. If you tell me, because I've separated men and women, so if you tell me it has he in the title, well, all the men had he in their title and all the women had she in their title. It's not a big deal. So that on the x-axis, what I'm showing is the correlation with the percentage of, or the correlation of the word with whether or not they're a female or male. Okay, so all the females almost all of them use the word she, and almost all the males use the word he. They might choose he or his or him, but one of those. And then we can zoom in down here. These are going to be like the proxy words. So these words are going to be not very informative at all. They don't tell you anything about somebody's job, whether they're a man or a woman. But they do tell you, but they are different for males and females. So let's zoom in. And what we see, there's a lot of words here, sorry. But we see some of them what we see are names. So like names are similar to he and she. They tell you somebody's gender, but they don't really tell you much about their job. And then you have other words that people talk about, like vulnerable, so this, or grandmother or something like that, pregnant. They'll tell you that somebody's a woman, but won't tell you anything about her job. And similarly, you have words for men. Well, let's say men will always put in their job, or not men, but it'll usually be a man if he says he's well regarded in his field. Men will write that in their bios, and women will write that at a lesser rate. So anyway, you can kind of see the words and look at it. It's interesting. We have a demo here when we pasted in Melinda's Gates' bio into our demo, and we can ask it to predict her title, and it predicts that she's a teacher. And you can see the neural net. It can see the weights, which words it's looking at by which they're more red. So the fact that it has the word work in such a red color means that was useful for the neural net for some reason. And it's also got the words like her in a little bit of red. So it's using that information. And we can see that also if we change her pronouns to his or he pronouns, or all her female pronouns to male pronouns, it all of a sudden predicts that she's an attorney. So I think you don't want a system that's making decisions in this way. And if you look across bios, you get consistently sort of male attorneys become female paralegals, male architects become female interior designers, and so on. Okay, so. Yeah.
Trivial ways to make the gender accuracy of 0 just yes.
Yes. Good. So yeah, that's a good point, Adam. You're saying one way to equate, to make sure that everyone is treated fairly, is to randomly assign them a label. And that's one extreme, and we'll have an algorithm exactly in that direction at the end where we will be able to move on that curve, and we'll be able to kind of get somewhere in between, right? It's a trade-off between our accuracy and the fairness. So that's exactly, and it's going to be a simple algorithm. You could probably guess what it is. Okay, but before we go there, I want to say that it wouldn't be satisfying to me, at least, to just to cover gender. It's easy as a mathematician or a computer scientist. That's the first thing you think about. It's balanced and stuff like that. But honestly, if I look around this room or in general, there's probably a bigger problem with race than with gender. There's certain races that are just not represented well at all, and there might be more discrimination against them. Or at least we want to cover everything that we can, age bias, all those things. So what are the biases? And when you try to define them, that's tricky. I mean, you can look at the census data. We can look after the fact that the census data, but they only cover 4 races. They don't have any religion data. It's very limited. But we can use a word embedding actually to help us find the biases, which is great. So what we do is we can take a huge list of names. You can actually find the names in the word embedding. But if you look in the word embedding, there are the names in part of the space. And then there's we cluster the lowercase words, and they cluster really nicely into like food-related words and job-related words and everything. So you can but let's just start with the names. We use this structure to identify the group. So we start with the names. We look at the embeddings of all the names. And we cluster those, okay? And you get these clusters of very meaningful names. Well, they're demographically different is the important thing about these clusters, okay? So, can you guys guess where Pedro would be in this group? Which cluster? With Miguel. It says Pedro's wife. Well, she would know. Pedro, can you guess where Carly would be? This is harder. There's a bunch of female clusters. There's a bunch of names that are female, and they differ by sort of age. Kayla, that's a good guess. It turns out to be over there. How would you know? But actually people, when we evaluated them, were able to guess this with some degree of accuracy. It was interesting. And, Brendan, you're there. So I put many of the I went to the directorate webpage and put the names that I found there on this thing. And you can see, first of all, you can see something about the balance here. It's actually got a fair percentage of females from that page. But there's certain races that aren't represented at all. And what we see here also is sort of like there's an African-American cluster male and an African-American female cluster. If you make enough clusters, you get what's called intersectionality, which means exactly this intersection, because it's well known that there's discrimination and stereotypes and problems that people face for being at the intersection of different protected groups. So anyway, the clustering works pretty well. And then what we can do is we can now rotate the embedding. So remember, we have this 300-dimensional space. We have the names over here, and the food words over here, and the jobs over there, and the crimes over there. We can rotate it so that the names are in front of the, let's say, food words, for example, and then we'll see the overlap. And so let's do that now and see if here come the food words. And what you see is that, sort of there's a big group. I'm over here with a lot of white guys, and we like beef and beer and hams. Pedro's group is the tortilla, salsa, tequila. And Carly's got the wedding cake, cupcakes, and yummy. It's a lot of stereotypes, and it kind of makes people laugh because it's kind of funny. It can be offensive too, like you have the African-American names with fried chicken. And so this is okay, this is interesting, but much more concerning is the profession association, okay? And it's, fine if my wife is in this cluster and, the Jewish names. It was interesting that it pulled out religion at all, and they're venture capitalists. Okay, that's good. But if you're in another cluster and the word embedding thinks you should be a cashier or a jailer or a cab driver or something, you may not be so happy, right? It shouldn't have all these associations between names and jobs and genders. And so this is helping us understand. So somebody comes to this embedding, one question they may have is just, what are the biases? What if you had a data set of Indian names? Maybe there would be castes or something. You may not be familiar with this data set. So this can be just a tool, first of all, to help understand what are the biases in my data. Okay. Are there any questions about this? Oh, if you want a billionaire child, yes, you should name them Randall. Yeah, names, might have an advantage. Okay, yeah. And again, we've got this way of looking at things. We found using these properties of proximity and parallelism, right? The proximity tells us all the clusters, and which helps us both define the groups of names and the groups of words, the lowercase words we use, like these job titles and stuff. And also the parallelism, so we're really capitalizing on the parallelism to say, hey, why do we have this parallel structure here? Why are these words closer to those names? And we're really taking the difference. So when I said rotating the two, what I'm really doing is I'm taking all the names and subtracting off the mean of the names. I'm taking all the food words and subtracting off the mean of the food words. So this is very analogous to the analogy stuff we had at the beginning, right? It's just the k-wise, where k is the number of clusters, k-wise version of an analogy, kind of, but with 12 different groups.
Did you say you were subtracting the mean of food words?
For each cluster of words, I call them food words, but we clustered, say it again?
Are you talking about the arithmetic mean?
Yes, when I talk about the mean of a bunch of vectors, so each of these things actually located in 300 dimensions. But if it was in two dimensions, the mean of a bunch of words just means the centroid, the center of mass. So taking the mean of the vectors, it means the average, if there are 300 numbers, it's the average of the 300 numbers for each one. Good question. Any other questions? Okay, then you can evaluate this. So first of all, you can check after the fact that these clusters have very different demographics. According to the census data, at least, the names are very different in gender and race and so on. One of the challenges was trying to compute a p-value for this, whatever that even means. And so what we did is we kind of tried to say, are these strengths larger than we would expect if we randomly rotated? We would keep the names fixed and randomly rotate all the other words in the embedding and do a Monte Carlo simulation and see how often we got such larger inner product triples. We can also do a human evaluation. So we asked people in the crowd first to see if they could understand these clusters. And they were actually able to do about a third of them, or maybe close to half, somewhere between a third and half of them were able to get pretty high accuracy on which of these 12 clusters of names this name belongs to. They would say Carly, then they would identify which of those clusters Carly belongs to. I was really impressed. And then those people who were doing well at that, we could, because we first tried without doing that, and many people just couldn't recognize the difference between those clusters of names. They were just a bunch of names, and then they had a hard time understanding the biases. Fair enough. But for some set of people, they could actually identify the differences in the names, and then those people were very accurate. They were depending on the embedding, but they were 70 or 80% accurate, the wisdom of the crowds, at identifying. We would take one of these clusters of words. So we would actually take, so the people who could understand these clusters of names, right, and predict which words go where, which names go where, we would then show them a group of words like maybe kosher, hummus, and bagel, and say, okay, which of these 12 groups does it go to? Well, that one may be easier, but then we say brownies, cotton candy, and pancakes, and they have to decide which of these groups, and this is like the really young female names probably, or something like that. I don't know exactly. Maybe it's the young names in the embedding. I don't know exactly, but the people could figure that out, and they got that. The wisdom of the crowds would get that pretty high accuracy. And many of the associations were deemed offensive by the crowd as well. Okay, does that make sense? All right. And some of them are super offensive, and so we struggled even how to present it, because we found if you put a list of names on top of some of these associations, that's really mean. I mean, the person sees their own name next to some awful crime. So instead what we do is we say, okay, these are the ones that the crowd said are most offensive, and if you want, you can go look, and look in this table to see which names are associated with. So one of the things that's kind of interesting is in the news data, the associations are usually about crimes. The awful associations are about crimes. In the web data, you actually have the N-word and other offensive terms that are associated. So the embeddings are just spitting out their biases in a sort of, some of them are okay, but many of them are terrible and awful, and in a very blatant way. They're just doing that, which is in some sense good. That is what you want from a system, because if it can enumerate its biases, then if you can at least, you'll know when you'll be able to fix it, or you'll know when you don't want to use it. So people should be careful before they just go ahead and willy-nilly use these word embeddings. Okay, and now I'm going to just describe a very simple algorithm that's going to try to address these biases. Okay. And that's the fourth part. And assuming that you're okay with this notion of I want equal accuracy on the different groups, then maybe a natural thing to do is try to balance the accuracy. If you have data, now we're back in the setting, not in the word embedding setting, but we're in the setting where you have data, and you want to train a classifier that tries to get about equal accuracy, not only on men and women, but people of all different races and ages. The previous approaches, and now these slides are due to Alexei Romanov, the intern. The previous approaches, one of the challenges is that they didn't know what the sensitive groups are, or some previous approaches actually do use the sensitive group. So what we're going to do here is we're actually going to use we're going to use the names to define the sensitive groups and use that in training time, but at test time, we're going to classify everyone's bio equally, not using their names and pronouns. Does that make sense? So we use the protected attributes for training, but not for testing, not for classifying people. And this approach, we want to try to cover many of these different features in parallel. So first of all, names, these clusters of names do differ, as I said, but Alexei made a very nice slide to show you how they differ by gender and by race, and you can see that there's some clusters that are highly male and some clusters that are highly female. And there's determining race from names is also, both of them are a guessing game, but it's a bit harder. And unfortunately, our data is mostly white. So we have a couple clusters that are not white, but it made it more of a challenge to even estimate the accuracy on for people of other races. So the algorithm we use is very simple. So we take a bunch of training examples, which consist of bios and labels. And we also have the names for the people in this data. And we're trying to learn parameters of our model, which is theta. And we're going to have a parameter, which we get to choose, which is the regularization strength. How much weight do we put on the accuracy, balancing the accuracies? So we're trying to minimize the loss. We're trying to choose parameters which have as little error as possible. That's very standard in machine learning. This is some crazy formula. It means maximizing the log likelihood of the data. It's convex, but you can think of that as just a replacement for minimizing the number of mistakes we make, right? That's what you would want to do in normal machine learning, is you want to minimize the number of mistakes you make, which is this L of theta. You want to choose the parameters of your model that minimize that. And now we're going to have an extra term here, which is called regularization, where we add a penalty which depends on the difference between the accuracy on these different clusters. So we're going to use what we just had in the previous section, where we define the groups that we care about by clustering. This is one approach. You say, okay, we have these clusters, choose some number of clusters, and now we want to have, we would like to have ideally equal accuracy on all of them, but as Adam pointed out, you could achieve that just by randomly assigning everyone a classification. But maybe you can do something in between where you still have high accuracy, but you have less, as we saw, we were able to get that before, for male and female. But now we want to do that for all of these clusters. So the simple algorithm is you cluster the names into k groups, and you consider the loss on a title-by-title basis. So for each job, you say, what is the loss for this group on this title? And then this term here is a penalty which says, okay, summed over all clusters, all pairs of clusters for each title separately, because we want to have not just equal accuracy for all different groups, but equal accuracy on each title for all different groups. So summed over all titles and we want to have equal, roughly equal accuracy for each pair of groups. Or this can also be written as the accuracy for that group compared to the average accuracy. Okay, so does that make sense? So very simple, and we're trying to minimize the average error plus this term, which is a measure of the difference in accuracy among clusters. Okay, so if you started with a bunch, so you need to be able to determine the names of the people in this data, or you have the names, we're assuming. But if you have names, you don't need any labeled data about their races or anything like that. The computer is using the word embedding to try to identify what are the groups of interest, and then it'll try to balance the accuracy among all these groups. We have another algorithm which is slightly more sophisticated. Instead of clustering explicitly, some of these dimensions might be, you have to make a hard choice with clustering, but if you just have these vectors, you can talk about the correlation between the errors and the name vectors. So you might want to say the intuition behind this algorithm is you don't want to have your errors correlated with any direction in the embedding. So look at the embedding of the names and look at your errors. And this is a bit more sophisticated, but can maybe protect certain smaller groups that wouldn't have been identified by cluster or thing like that. You want to say, look at the average error and the average name direction, and you want to say the error is not correlated with the names. Does that make sense? Okay, and you minimize, again, the same thing with this regularization parameter. And what you get, as you might expect, I'm showing it to you on a different data set, actually, because it worked better on a different data set than the BIOS data set, but I'm happy to talk about that more at some point if you want offline. But what you get is as you increase the R parameter, which we're showing by making the dot bigger, as you increase the regularization, the accuracy goes down slightly, and both the gender accuracy gap and the race accuracy gap, so we try to estimate with the names, which as best as we can, the gaps we think we have in the race and the gender, and they do go down a fair bit, and there's this trade-off. Does that make sense? So you're balancing. On the one hand, you would like to have equal accuracy. On the other, for all groups. On the other hand, you'd like to have high accuracy for all groups. Okay. So there's several interesting questions that you might be wondering about. So one of them is, this is not, these are more than clear. Sorry, 1 second. I have my slide. Let me try to get it here. Well, let me just tell you what the open problems are. So one of my open problems is asking about other languages. Another thing we didn't do with the vectors is we did not figure out a good way to remove bias from these multiple name clusters. So we tried to do that, but we weren't able to. So in he, she, we can just remove the direction he, she, and that seems to work pretty well. But we didn't actually have we used the embeddings of the names to identify the problems, but we didn't find a good way to create a word embedding that's less biased in all of the races. the most obvious thing to do is to do some kind of principal component analysis and remove many directions at once of the names, but in some weird ways it seemed to amplify the biases. So anyway, there's still a need, I think, to create a nice, less biased embedding for all kinds of names and races. So that's kind of an interesting open question. And for, in general, for the bios, there's all kinds of interesting questions about, is this the right notion of fairness? And I think there's all kinds of interesting questions you can ask with this data beyond what we did. Another question that's very important is about ranking people. So we were talking about, from the person's perspective, or the advertising a job to a person, which job do we choose to show them? But there's a question about ranking people. What if you're ranking people, things get even more complicated? So in our system, for simplicity, in our data set for simplicity, we said, oh, what's the right job? And the best decision would be just to give everyone, obviously, the title that we have in the data. But if you're ranking people, it gets even more problematic, but it's also very important for real world. So the questions get hairier as you think about more and more realistic settings. So it makes sense, we think, to start in the simple cases. But in conclusion, I guess I would say, as I said, the models that you fit to human data will show human-like biases, and we don't want that for good reason, because you want to avoid compounding these problems, amplifying the biases, or making the gaps bigger in the world. And another good thing about these word embeddings is we can use them to try to help identify what are the groups that might be at risk. If, typically when somebody does a census or something, they think of like 3 or 4 races, but the word embedding can actually identify all kinds of fine distinctions. And then, yes, I believe, I'm optimistic that we can eventually, I'm not saying our algorithm is the best, that we can eventually have classifiers that balance accuracy across all groups. Now, one of the open questions that I didn't mention is about having explainable classifications. So that's something that I think would be nice. It would be nice if your classifier could not only say, okay, this is what I think your title should be, but why? And that would help us design and debug and get confidence in a system. And in the biggest picture, I think there's a nice, exciting new area called responsible artificial intelligence that I've become familiar with because I have a bunch of interdisciplinary colleagues. So this is an area that involves people in, legal scholars and sociologists, and people who think about all kinds of ethical aspects of things. And it's a really exciting and interesting area because it involves so many different people thinking about these problems from different areas, and artificial intelligence researchers. And I encourage you to look into that area if you're interested in it. And that's it. Thank you.
So one request, if you'd like to ask a question, and if you're not too far embedded in the middle of the seats, if you could use the microphones. There are the microphones on each side of the aisle. Yeah. Any questions?
Hi. Can you comment on how sense-disambiguation might affect the results of this, or be useful as a tool to further this? Like words like server or runner?
Right. So that's a great question. So many words have multiple senses, like the word bank. It could be a river bank, it can be a bank, a financial institution. And one of the things that's not obvious is that word embeddings should work at all, right? Because so many words have so many different senses. But it turns out that by and large, they work quite well. Even the word nurse, right, which I'm proposing is gender neutral because it shouldn't be male or female, but has a sort of nursing a baby has a gendered association. But so people have studied that in great detail and have come up with better embeddings, or embeddings with multiple senses per word. So that's one way they try to deal with it. And actually the latest and greatest type of technology for embedding is that they compute a different embedding for each word based on the context of the words around it. So they don't just embed, they don't have one embedding for a word, but they would say, okay, the word bank used in this context has this embedding in this context. And they get much better results with that, so exactly in that direction. And figuring out how to be fair with one of these newer type of embeddings, which just came out in the last couple of years, or last year maybe. It's a big arms race between all the big companies. That's a great question. But that's how they address it right now, is with a context. Any other questions?
Let me ask a question. So you've thought about how to train computers and algorithms to have less biases. How about for people? Do you get any insights about how to get people? And for instance, the people who are really good at assigning words to groups, do you want them making decisions, or is it because they're relying on heuristics that would actually cloud their judgment?
That's a great question. Yeah, I don't know. It's much easier to see the biases from the computer system than it is for the people. So with people, they have something called the implicit association test. I don't know if you've seen that, where you can't just ask somebody, what do you think? You can, but many people will say, I'm not biased. I don't have a strong opinion. But they give this subtle test where they time people, and they have people putting words in different groups. You can test, if you just search online for implicit association test, you can take one of those tests. And pretty much everyone shows up as biased. But you're right that I actually have no idea. That's a very interesting question, how people would differ, those people who can identify the name groups and those people who can't. I guess your question is, if you can't identify the name groups, maybe you can't be biased against them. And there's some biases that you won't see from language, right? Like against short or tall people, maybe that won't show up. And if you're blind to the differences between groups by names, then maybe you won't be biased. But it's a good question whether you can use these tools. I mean, there's a group of people who are studying using these tools to understand how biases change and differ across societies or change over time. So that's a way to do it. But in terms of, I don't know how to change people's perspectives. That's a good question. I haven't thought about that.
So you were looking at gender and race bias. Did you look at any other kind of bias, for example, age bias?
Right. Yes, so these different clusters of names, for example, I'm not showing you that data, but we have that. These different groups of names definitely differ by age and religion. So this one here is a bunch of Israeli Jewish names. My wife is there, my family's there. And then these female clusters differ a lot by age. Is the biggest difference. So it actually picks up on that, even though we didn't give that as a feature. It wasn't input to the system at all. And it'll pick up on a group. If you do more clusters, it'll pick up on a British bias. There's a big direction in the embedding that separates sort of British English from American English. So it picks up on a huge variety of biases. Great question.
I wonder what, it's hard to imagine how you could do introspection on a word embedding. I wonder if you've got some thoughts about how you would actually do. I mean, if you wanted to quiz it about what was how it was making the associations.
Oh.
What would you actually?
Oh yes, that's a great question. So you're saying maybe these are the biases it has, but where did it come from? Is that the question?
Well, you said that you were interested in finding ways to be able to quiz the.
Well, what I mean is, if it says, if the thing says, I think your title is a software engineer, and then it highlights your name in big red letters, then you say, well, oh, okay, you think I'm a software engineer because of this word. So that's one way of the computer explaining its decisions. Does that make sense? Of inspecting it, but maybe there are other ways that are much better.
I guess I was looking for thoughts you had about what that might be. Something more than just highlighting the.
Yes, that would be. Computers in the future, they're on track. There's really been recent breakthroughs on computers like just generating English text, or in any language, but generating natural language. It's possible that it could generate an explanation. And if your goal is to explain it to somebody in English, that's one way. But I don't know. It's a great open question of how would you like to? How would you like the computer to explain its decisions? But anything is on the table right now. We don't really know.
I think his question is you learn an embedding, so you learn this point in the space, and he's maybe wondering how you get back to the parts of the corpus that were most important for generating that point.
Right. Those are both great questions, and people are kind of trying to understand, studying both of those. So there's different ways of explaining models' decisions. Sometimes what they do is they show you other similar data, other people's bios that were classified similar. Here's a bunch of other people who were programmers we know. Sometimes they go back to the original source text and they will try to pull out some sentences or articles, or it's a wide open area right now. Nobody has a great idea, but it is interesting to think. I think both of those are being asked. Where in the source data, if the data is a word embedding, where in that data? In both cases, we're getting biases here. In one case, we're getting the bias, let's say, from the news or the web. In another case, if we're training with previous bios, the bias is originating in that data, right? So both cases, you want to kind of know where it's coming from.
Is there some methodology for enumerating the types of semantic predicates you might want to mine from a vector space that are relevant for bias?
What do you mean? What type?
Well, so, I mean, you have these relationships between
right,
food
words,
like foods
yeah,
and like
yeah,
ethnic group.
Right.
So that would be a type of
yeah,
predicate.
Yeah.
Like,
what we did is we just clustered all the 25,000 most common English words into groups, and that gave us food and profession and crimes. But we clustered them maybe 50 or 100 clusters, I don't remember. And so that was how we did it. But you're right, some of them are maybe more problematic than others or more interesting than others. So you could imagine adding to that a step where people are saying, yeah, this is interest. Can the computer learn what would be of interest to us? Is that what you mean?
yeah.
That would be really neat too. And people in other domains are trying to do similar things where they're asking the computer to learn from humans what is of interest.
Two more questions, please.
So the human is adaptable. We've survived the Darwinian process to evolve to where we are.
Mm-hmm.
And you've now told us that if differences are measurable, that we can ascertain what they are and then try and remove the bias.
Right.
How long do you suppose society will take to adapt to everybody having the same name?
Oh.
Remove the bias.
Yeah.
It's obvious that society will adapt.
Well, I mean, one thing is that we're not actually removing the bias from society at all. We're trying to not have our classifier amplify that bias.
If you use this tool to hire
Right.
people,
Yes.
in 100 years, people will all have the same name.
People can, yes. I mean, this is about, that question that Pedro had. You can strategically name your child, right? Or if the world is very biased. So the world is biased, so you can be very strategic right now. If in an ideal world things are less biased, I don't think we'll ever remove it entirely. But if things are less biased, then that strategizing would be less useful to you, which is, I think, good. So hopefully the adaptation of the world will be that you won't have as much of an advantage for certain kind of irrelevant features. Does that answer your question? I'm not sure. It sounds like a very neat question.
One more question, please. There is one.
So these word embeddings are kind of the state of the art for language processing,
Mm-hmm.
like neural networks and stuff.
Right.
Is there some other technology that's out there that is gaining speed?
That's it again?
Some other technology for doing, is there like some other thing that's coming?
Well, what I mentioned is that the word embeddings with context, that's the newer, the latest and greatest. So they use the surrounding words to get the word embeddings. And the deep neural networks, which we've also trained, I didn't really go into that, but the demo I showed is actually a deep neural network, which means it's not, it's pretty clear that the answer is not to just average the vectors of all the words, but that's still kind of something that works really well in the state of the art, but we know that in the future it's going to be something much more complicated than just averaging. So the vectors of all the words. But I don't really know, I mean, maybe somebody else has another answer, but as far as I know, this is kind of the main approach that people are taking, and I haven't heard of anything else that's anywhere near as good.
Okay. Thank you
Thank
very
you.
much.